All right, so I guess we'll get started here. It looks like we're just around 1 o'clock. Hello, everybody. My name is Rollin Willis, and I manage the SOLIDWORKS for Startups program here in North America. Really appreciate you taking some time to join us today. This is the third installment of our Simulation for Startups series, and today my colleague Hassan Krem, Hassan, forgive me if I mispronounced your last name, but he'll be covering the electromagnetics role, which is one of the many tools that are available within the 3D Experience platform. So the 3D Experience platform, just to give a quick overview, provides a wealth of capabilities to help you validate your product designs, including tools that we aren't discussing today, but have in the past, CFD, linear and nonlinear analysis, of course, electromagnetics, which we're covering, plastics and motion, which are just a few. It's a very broad portfolio. So, and we understand that startups don't always have the luxury of time and unlimited funds. And the SOLIDWORKS for Startups program is really focused on providing you, those startups, with the best tools available to achieve your product development goals and help to reduce the strain on your already limited resources. Now, bear in mind that the capabilities that we're covering today are available to participating startups at either no cost in our early stage or at significant discounts. So for those of you who may already, who may be interested in the program, this is a 3-year program for early to mid-stage startups who have been in business for less than 5 years and whose funding and or revenue is less than 5 million. So if you wish to learn more, please reach out to me via email. I'm more than happy to help and look forward to chatting with you. So with that, I'm going to turn the control over to you, Hassan. Hassan, the floor is yours.
Thank you, Rollin, for this introduction. I'm going to share my screen. Here we go. All right. Can you see my screen, Rollin? Could you confirm, please?
I can see it just fine. Thanks very much.
Perfect. Thank you. So hello, everyone. Thank you very much for having the time to join us for this webinar. So my name is Hassan Shraim, and actually it's pronounced Shraim, but no worries, Rollin again. And today I'm going to show you our electromagnetic simulation capabilities, which uses the product that is called CST. And CST stands for Computer Simulation Technology. And throughout the presentation, I will show you what are the domains of simulation that we can cover with the tool. And of course, for each application, I'm going to just give you a small example. But of course, the list of examples that you're going to see today, it's really non-exhaustive. We have a lot of examples, that are dedicated for several domains. And of course, each domain can cover a lot of industries. So if you have any questions, as Rollin said, do not hesitate to get in touch with us, and we'd be happy to answer you back. So let's start with the introduction, and we're going to speak about what is electromagnetics. Usually, electromagnetics phenomenon, it's something that you can see every day, even if you don't notice. When you wake up in the morning or at night when you turn up the lamp or you turn, you turn the light on, that's an electromagnetic phenomenon going on in there. Also, when you take your electric car and you drive it, you have an electric phenomenon that's pushing the motor to turn and to push the car forward. Also, all kinds of communications, they use electromagnetics to ensure that we have a stable communication, especially throughout the antenna, which is the key element in all kinds of connectivities. And finally, we can manipulate light, because light can also be considered as an electromagnetic wave that we can manipulate using several devices, that we may see. For example, we have here this imaging machine that we use in the life science industry, and it uses electromagnetic waves that go through the body and tells us if we have a problem inside or not. In the meantime, I'm gonna just put my pointer in this, like this, so you have a better view. There we go. So as you may have seen it here, the simulation, the electromagnetics portfolio or the electromagnetic spectrum is really broad, because we can cover static, where the electromagnetic field does not have at all a dependency on time. until the light wave, of course, passing through the hertz, the kilohertz, megahertz, gigahertz frequency bands. Now, if you ask yourself, why do we need simulation? Because probably like 10 years ago, a lot of companies, they would fabricate or, just prototype their product based on probably some mathematical equations or probably on some theory. Well, this was not enough because even until 10 years ago and even now, we have a lot of companies that they fail to meet the requirements they already or they build their prototype to operate at those specifications. But despite that, when they go to the measurements, they have bad surprises. In addition to that, we have an increasing challenges regarding the complexity. If you take a mobile phone nowadays, it has a lot of antennas, for example, especially that every now and then we have a new protocol. For example, the most recent one was the 5G, but in the future, we will definitely see the 6G protocol come into life again. And we are tending more and more to minimize or, to make miniature prototypes. You see, we increase the complexity and we want our devices to be more and more small. So this is really a big challenge. And using some materials that have like, I would say, exotic properties, and the fact that we are tending again to make our structure or our devices smaller and smaller, this could increase the risk of interference because, again, if I take the example of a mobile phone, you may have a lot of interference between the mobile phone, between the antennas that are inside. And this is where the simulation is really important because, first of all, it will help you with prototyping, but virtually. We are literally doing what we call the virtual twin. The mobile that you see in real life, you can exactly reproduce it by a numerical, let's say, device, okay? And doing that, you will be able to do a lot of design changes. So you see, okay, I want to change the position of this antenna. I want to modify its size. I want to modify the material. So you see, you can change whatever you want without any extra cost. And this helps you with optimizing the product without going to prototypes after prototypes after prototypes. So you are saving a lot of time. You are saving a lot of money. And most importantly, you are eliminating all risks, and you are having by your side a friend that will help you with, making your decision. Okay. And of course, since you have a tool that is capable of showing you what you cannot see in real life, which is the electromagnetic fields, you will also have the possibility to innovate. You can even push the boundaries of your products and make it even more and more innovative. So what are the applications and the domain that we can cover with our solutions? Before going into that, let me just starting by speaking a little bit about the technology that is used. And as I told you, it's called CST Studio Suite. And it's a tool that is composed of one graphical interface, one GUI. And inside this GUI, we can cover a lot of domains. We can cover high frequency, as I told you, the low frequency, the particles, the thermal simulations, all of those, they are integrated within the same interface. And for this reason, our tool has more than 25 numerical methods where each one of those methods are dedicated to a certain domain. So you will not, we got you covered regardless of the domain that you need to discover. And in addition to that, we can do some, as I told you, some multi-physics simulation, because when you speak usually about electromagnetics, some devices, they dissipate a lot of power. Take as an example, I don't know, for the gamers among us, when you use a game that needs a lot of GPU power, a lot of graphical process unit power, you may hear that at a moment there is a fan that starts turning inside your computer. And this is to evacuate all the heat that is produced by your GPU. So here we can simulate that because all the components of your PCB or of your GPU, they are dissipating a lot of power, which is going to create heat. and you can study what we call the cooling. But of course, not only of PCBs, but you have a lot of designs that may heat. For example, sometimes we can create heat on purpose, especially like for those like probably you may have used before, you know, the inductive stoves. You see, if you put your hand on the stove, it will not heat. But if you put the perfect material, which is a magnetic material, you can study the electromagnetic phenomenon, but also the thermal behavior of your device. And I know a lot of companies that they use literally what we call the magnetic heating. And this is something that we can do inside our tool. So anyways, without losing a lot of time, here are the 4 applications that we can cover with our tool. First of all, as I told you, we have the low frequency. So here you have some really small examples of what we can do. We can deal with sensors, we can deal with MRI machines, we can deal with electrical motors or even generators. And then we have the high frequency. And in high frequency domain, usually the electromagnetic field that is produced by the device, is meant to be radiated. And this is why an antenna, it's definitely a high frequency device, because the signal that you inject in your antenna will be radiated, you know, that, and this is what actually helps us with communicating with friends or probably on the internet, etc. Then, of course, we have the electronic domain, or what we call the EDA, electronic design automation, where we can study what we call signal integrity and power integrity to see if we have, you see here, this is an example of a PCB board, and you have a lot of component on it. You see those components, or these IC chips that are made of silicons. They need to communicate between each other. You know, you can have your CPU that is sending a digital signal to your memory, and the SI simulation helps us with seeing if the signal that has been transmitted between the CPU and the memory is not deformed, right? Because the memory need to receive the good information, yeah? And in the same time, you have the power integrity simulation, or what we call PI. It means we need to ensure that all the components on the board, they are receiving the good power that makes them operate, you know, perfectly. And now in the electronic domain, but not only in electronics, of course, we have the study, we need to study what we call the electromagnetic compatibility. You will see that this is something very important, and I'm not gonna explain it here. I will wait until the good slide to show you what it's about. And finally, we have the electronic cooling, because a lot of printed circuit boards, they tend to heat, and we will have to find solutions to reduce the temperature rise, such as putting, like, you know, heat sinks, or putting fans, or even water pipe, you name it. Finally, the most exotic domain that we have is the CPD, or what we call the charged particle dynamics, where we are studying the interaction between the electromagnetic fields and charged particles such as electron, protons, etc. And, you know, just to show you, this is an example of an accelerator cavity. And the, you know, biggest example that I show you, that I could tell you about, is the CERN, which is the biggest accelerator, and it's called the Large Hadron Collider, and it's in Switzerland. And those guys, they use our tool to design and optimize their cavities. Okay, let's start with some applications in the low frequency domain. And there you go, we start with sensors. So how sensors work? If you take, for example, your connected watch here, and sometime under like probably perfect lighting conditions, you may be able to see that under the screen of your watch, you know, you have some metallic grids, as you can see here. And those metallic grids, they are charged with a voltage, with a given voltage. And they have an equivalent capacitor. Now, when the user comes and places his finger on the screen, he is modifying the property of this capacitor. And then the CPU of the watch, the processor, as you can see it here, because we can couple 3D simulation to a circuit simulation. This helps us, or this helps the CPU of the watch of knowing where the user has placed his finger, because depending on where the user has placed his finger, there is, you know, there is a program let's say, or this is, like we call this fourth generation programming or FPGA or whatever, it's embarked codes that allows the CPU of the watch to know where you have placed your finger and later on do the command that you need. A second application is the electromagnets. Probably this is something that we may have seen in school. It's basically when you have a magnetic material such as any iron nail or screw or something like that, when you wind some copper wires around it and you drive a current in there, you are creating a magnet. And an example of real life magnet or real life electromagnet that is needed a lot in the industry is the structure you can see here. And this is what we call the quadrupole. And you can see here, we have a magnetic material that is made of steel here. And in the same time, we have coils that are wrapped around here. And we are driving some currents inside. And this is how you create a magnetic field. And you have a lot of application for this. You can use it in accelerators because you want to focus the electron beams inside. You can use it in speaker, if you take a speaker by the at the back of the speaker, you have a magnet. This is why you can stick it on a metallic like door or something. But we can use it also in industrial machine, and especially we can use it to lock doors. We have a lot of doors right now or today's that are locked using magnetic force, right? And when you click on the button next to the door, you are actually demagnetizing this, and this is how the door opens. Another type of low frequency application is the wireless charging. You may have heard about induction charger for mobile phone, but nowadays, since the cars are being electrified, induction charging also exists for cars. If you go inside like very recent charging station, either you can charge your car using the wired, technology with the plug, but some stations, they have this, they have a coil that is on the ground, and we drive a high current inside this coil. And in the same time, car manufacturer, they are integrated a receiving coil. They integrate a receiving coils, or what we call the secondary coil. And here we are just transferring the power from the first coil to the secondary coil that is in the car. And of course, behind you have like charging units, you have some voltage regulator, and then you drive this current to the battery to charge it. Okay. So same principle as the induction charger of your mobile phone. And of course, we can deal with electrical motors and electrical generators because, motor, what is it? It's composed of two parts, a rotor and a stator. For example, you inject again a current with a certain way, we call this the three-phase. A three-phase current you injected on the rotor, you create a magnetic field. But by of course, you have a force that is applied on the rotor. And this is how you make your motor turn, right? This is the motor part. And on the same time, the generator part, it's the complete opposite. Why? Because you are moving your rotor, okay? It's the movement of the rotor that is generating electricity. So it's completely the opposite of the motor, okay? And we can deal with any type of motors, whether they are permanent magnet, asynchronous, switched reluctance, you name it. And of course, when we speak about motors, we have to consider several types of specific material. We call that the magnetic material, and especially the nonlinear material, where we can consider what we call the hysteresis loop of the material. The complete hysteresis cycle, we can consider it. And of course, this helps us with calculating accurately the losses that are inside the motor. And we can couple this to a thermal simulation to see how the motor is heating up. Well, speaking about heating and low frequency, I'm going to show you a real life example of a transformer. A transformer. I'm 100% sure that you must have seen this before. Transformers, they exist in single phase, like the one that you have here, or three phases, right? So in single phase scenario, you have two coils. Again, one primary and one secondary. But in three phases, you have two coils per phase. So as a total, you have 6 coils. And usually transformers, they are used to step up the voltage or to step it down, which means to increase it or to decrease it, if you want to speak in a classic way. Now, how it works, usually you have some coils, the primary and the secondary, which are winded around a magnetic material. Again, it could be an iron or steel. And a very important, usually transformers manufacturer, they make sure that their transformers, they have to handle a lot of, we call this in case of default, like a short circuit or something, temperature can increase quite quickly. And those guys, they want to make sure that their transformer will withstand this amount of temperature. And this is the example I'm going to show you here. So as you can see, this is my transformer. I have the primary coils in orange, and I have the secondary coil in green. And I would like to run the simulation where the secondary currents, I have a fault, so I have a short circuit. And there you go. When we have a short circuit, what is happening in reality is that you are draining a lot of current from your source. And, usually you are increasing the losses inside the coil. You are dissipating a lot of power. And this what actually makes your transformer heats like crazy. And this is something that you can see here. What I've done here is that I coupled the losses that I've calculated in the electromagnetic simulation to the thermal solver, and I was able to calculate the temperature increase after 3 seconds, because this is what the standards wants us to do. If you want to test the strength of your transformer against temperature, you have to inject this high current, or you need to do the shortcut or short circuit simulation for 3 seconds. And you see here, I have a temperature that rises up to 272, which is quite high. And you can definitely couple that to like a mechanical solver from probably you may have seen the webinar that has been hosted by my colleague Reza some weeks ago. So this temperature, you can couple it to a mechanical solver to see how this temperature could destroy, eventually the component of the transformer. And since our solution, it's 100% fluidic, you can literally see the airflow around the temperature, around the transformer. So you can see here the velocity of the air. And you may even consider that you have a fan that will heat or that will cool down your transformer, and see, for example, depending on the flow of the fan, on the airflow, etc., you can see how this temperature change. Okay, I'm gonna switch gear now and go to the game to the high frequency applications, and I'm going to speak to you about a game controller, which is, it's a cool application. But before that, if you ask yourself why we found antennas, because I'm going to speak about an antenna here, well, the simple answer would be everywhere. Today, everything is connected. Even the fridge into your home could be connected. Any type of home appliance could be connected. And to be connected, you need an antenna in there. So this is an example of where you can find antennas. You can find this type of antenna on the fuselage of an aircraft. It's called the blade. This antenna here is called the shark fin antenna. And now when you go out and you look at the roof of your car, you will find this structure, I guarantee you. And this is an antenna. I think it has 2 antennas, one for the GPS and one for the FM receiver or the DAB receiver. And they are both integrated under this kind of radome. So you see here, the mechanical engineer, he respected 2 things. He respected the electromagnetic performance, but of course he also respected the aerodynamics. This is why the shape of the radome is like this, right? And of course you have the telephone, where you have probably more than 10 antennas in the recent mobile phones. But of course you can find them. This is an example of a satellite communication antenna that you can find under the radome of a drone, right? A military drone. And what you have here is is a wireless switch to switch on or off the light, instead of going through like, having a lot of wires inside walls, etc. You can just use this wireless switch. Yeah, you can see here that you have the PCB with all the commands, and of course here you have the antenna. Now, of course, I'm not gonna give you a lot of details on here, but we have no limitation in what we can do in antenna domain. I mean, we are literally the #1 leader, at least in antenna domain, in an antenna design. What you can see here, is a scaled down, of course. It's really scaled down, this structure, because we are dealing with a coverage of these two 5G antenna arrays. So here you can see them very close to each other, but in reality, they are like probably some hundreds of meters away. And they are placed at two different positions inside a suburban area of a city. And the aim here was, first of all, to study the couplings between the two antennas. You know, if one antenna is sending, if eventually the second one is receiving, but also we can study the coverage of the city. So we can do some, what we call some, not radio planning, but some antenna placements, because depending on the position of the antennas, you know, inside the city, or even if you have a private network inside your home or inside your factory, we can place antennas wherever you want, and we can see if the whole area of interest is covered, and if you are susceptible of losing a signal at a moment. Yeah. Good. Now, the thing of integrating, as I told you, when we are dealing with a lot of antennas inside one platform, like here, this antenna, this telephone, it has probably 10 antennas inside. So this is great because it increased what we call the connectivity of the antenna. But in the same time, you have a problem of increasing the risk of interference. And this is why we have a tool inside our software. It's called interference task, and you will be able to see if your antennas are interfering together. But not only the antennas, sometimes if you are sending here a USB signal, you know, sometimes you are transferring data from computer, from anywhere, and these data is being transferred through the USB signal. And believe it or not, this signal could be radiated and be captured by an antenna. And this is very dangerous because your data could be leaked. This is why studying the interference is super important, and we can do it. So here you have a remote control, you know, we have a game controller, and you have the PCB, you know, you have the electronics inside. So as you can see, it's super important to consider everything, yeah, not only the PCB, but also the casing, because the casing could alter the operation or the performance of your antenna. And we have here a chip antenna, you know, we call this a chip antenna because it's very small and it's easily integrated inside, you know, this kind of electronic board. And again, what you can see here, you can see how the energy of this antenna is radiated. You can see what we call the gain, and this will give the manufacturer an idea of the range of this remote controller, or game controller. Yeah, you can say, okay, probably you can tell the user that having this gain, you will have a range of 9 meters. So which means that if you go above 9 meters, your game controller will not receive any signal from the controller, yeah, or your console. But of course, when the antenna is radiating, some of the energy is also coupled to the electronic board. As you can see here, we have a lot of energy that is coupled to the board. And this is why this is so important, because if you see that you have a lot of energy that is coupled to the board, you may think that, okay, probably it's time to move the antenna around and see where you can place it in order to reduce this coupling and those interference between the antenna and the board. Again, now when we do any kind of connected object or any kind of electromagnetic device, whether it's low frequency or high frequency, we need to make sure that the human is safe. So human safety, it's really a concern for all electronic consumer producers or manufacturers. To give you an example, I have two small examples here, or even three. This is an example of a worker that is going to the top of the tower here. You know, it's a communication tower with a lot of antennas. And here you have the worker, and we wanted to see if we need to turn off all the antennas or not in order to ensure the safety. So we have run a study here where all the antennas are activated, so they are actually sending signal, and we wanted to see what is the energy that is absorbed by, or what is the power that is absorbed by the human body. And of course, you have some international standards that tells us that we should not exceed this amount of power. And this is what the simulation helps us with. So you can see here, we can literally study each organ of the human body and the amount of power that is absorbing. Another scenario, which is practically the same, it's here. It's a user that is using his mobile phone. And you know, the mobile phone, it's very close to the head. You know, you're literally putting your phone on your ear, right? And again, we can study the amount of the power that is absorbed by the human body. And for your information, we call this the SAR, specific absorption rate, and its unit, it's watts per kilogram. Another concern in human safety is the MRI machines. You may have heard before that if you have an implant, you know, inside your tibia, or you have a pacemaker, they ask you about this before doing an MRI. They don't ask you this for fun. They ask you this because the MRI machine, which is usually used for your own good, could be harmful. What is happening? This is a small example, and I wanted to see if this tibia implant is certified. Because again, those guys who are manufacturing implants, they need to certify their products. And how they certify their products? They run simulations. So here as an example, I have a human here that is inside an MRI machine. And this human, it has a tibia implant in his leg. And the idea is to see if this will cause heat, because this is the danger. The region around the implant could heat up. And here we are studying how much the temperature is heating up and if this could be dangerous or not. So if you have like implants, around implants, the temperature rises to some like 40 degrees or 41 degrees, it means that this implant cannot be used. It will harm your tissues. Okay? Good. I'm going to jump now to the third domain, which is the electromagnetic compatibility. And electromagnetic compatibility, actually, you know, guys, it's a very wide domain, because usually the electromagnetic compatibility, if you want to take the easy definition, what is it? It's to ensure that if you have a lot of electronic products, for example, imagine that today you go back home and you find out that, you know, in your room where you are sitting, you have a lot of electronics. You have your mobile phone, you have a TV, you have your laptop, probably you have some other components nearby. So the electromagnetic compatibility, or one of the electromagnetic compatibility study, is to ensure that all these equipments, they will still be operational together. Okay? And I will give you here why we run this kind of study and what are the studies that we do. So here, of course, I'm doing this electromagnetic compatibility study on the same electronic board of the mobile controller. Now, of course, this is a complete workflow, but I'm not going to lose a lot of time on this. I will show you each one directly on the example. So we see here, I'm taking again the PCB of my game controller. So I'm starting by doing what we call the power integrity simulation, yeah? Power integrity, as I told you, it means I have to make sure that all my components, they are receiving the good amount of voltage to make them operate. And of course, inside the PCB, you have some components operating at 12 volts, at 3.3 volts, 1.8 volts, etc. So here I'm studying the 3.3 volts. So you see, I have here the USB connector when I can plug the charger, right? So the charger is delivering 5 volts. Here I have a voltage regulator, and the voltage regulator is giving me a 3.3 volt to the CPU. And here I have another 3.3 volt that are going to the battery side. So you see the battery of the remote control or of the game controller is being charged by 3.3 volt signal. So the thing here is that if I zoom a little bit here on the area of the CPU, I see that I have a little drop of the voltage. I'm not receiving quite exactly 3.3, but I'm receiving 3.299. Now, of course, this device is perfectly optimized because 3.99, 3.299, it's very, I mean, we have very slight drop of the voltage. But in all cases, what you can do with the tool is that you can list here all the components that need, for example, 3.3 volts, and you can define a tolerance. So you can say that this component, if it receives like 1% less or 1% more than 3.3 volt, it's okay. I will still pass. And you see here, you have a report that tells you the components that are not operating good enough or not. And this has been done at DC, you know, at direct current, but bear in mind that we can also do it for AC, you know, for higher frequency. Now, if I want to, again, to study the signal integrity, here I'm considering that my CPU is sending a digital signal to the USB connector. So we have the possibility of emulating the behavior of the CPU through what we call the IBIS file. If you need more information about that, please do not hesitate to let us know, and we will gladly answer you. So the idea here is to see, okay, so this here in blue, I have the signal that is generated by the CPU. And here I have in orange, the signal that has been received by the connector. So you see, first of all, you may notice that we have a loss in the voltage. But in all cases, this is not really bad. Why? Because if you take this signal, you know, this orange signal, and you fold it on itself, you finish by having this kind of curve, and this is what we call the eye diagram. So some people say that it resembles to an eye somehow, and this eye needs to be the most open possible. Okay, and here I'm comparing the openness of the eye with respect to the specification that are represented here by this purple curve. So here, even though I have a loss of voltage here, I'm still respecting the specification, which means I'm totally fine. Good. I have to close this. Here we go. Let's pass to the next slide. Now, of course, we can run also some thermal integrity, as I told you, because some electronics, they tend to heat up. And here we wanted to see if the user, for example, has been using this remote control for a long time, if it will heat up a lot. So here we can consider the dissipation of power in each component, and we can run a thermal study. And you can see here that we can run thermal simulation on the detailed PCB. There's no need for simplification whatsoever. You take the PCB as it is, and you can run the simulation. And you can see not only the temperature rise on the PCB component, but also on the housing, yeah. And of course, as I told you, since it's a 100% fluidic solver, you can see what is happening around in the air. So you can see here, the temperature of the air is changing a little bit, but you see, we are going from 20 to 24. And the temperature actually of the remote control, it's actually rising to 39 degrees, especially if we are starting, for example, as at an ambient temperature of 20 degrees, we still have like 20 degrees of rise. But in all cases, you know, this is very close to the human body temperature. So let's say that the human won't be bothered by a long-term use of the remote control. Good. Now I'm going to speak about electromagnetic compatibility. And I promised you that I will give you a little bit of what it is. So if I take again this example here, when the USB, when the CPU is generating a USB signal to be sent to the connector. So this signal is meant to stay on the PCB. But whether if you want it or not, this signal will be radiated somehow. It will definitely be radiated. It's like that because the PCB, it's a very complex environment. You will have a lot of mismatching in the lines, etc. So the signal will eventually be radiated. So the electromagnetic compatibility that we study for this type of electronic products, we have what we call a one type, of course. This is a type. I'm not going to show you everything we do in electromagnetic compatibility, but one type is called the radiated emissions. And basically, it's the study of what is the amount. If I take, for example, here, this USB signal that has been transmitted, what is the amount of the radiated energy? Okay? And again, as I told you, even until now, 50% of companies or 50% of electronic products, they fail because every electronic products need to be certified nowadays, every product. And until now, 50% they fail. So this means a loss of time, a loss of money for the company, right? So here, how we study the radiated emissions. So again, you see here, I'm considering that my CPU is sending through this USB channel some information to the connector. And in the same time, I'm placing here some probes that will capture the energy that is radiated all over or all around the controller. So here I can inject the signal, it's the USB signal as I saw before, as we see before. You see here the deformation the signal is receiving. And finally, by doing this result in frequency domain, you can see here that I have spikes. And this is the result that we call the radiated emissions. You see, those spikes are actually measured by those probes that I placed around. And how we make sure that our device is certified, it's basically by seeing if those spikes that I have, they are violating these limitations in red here. And those limitations are actually the FCC limitation. It's this organization in the US, the FCC. It tells us that the radiated emissions from any electronic, that is used by consumers for civil application, it should not go beyond these red lines. And of course, they can go also higher in frequency, but here I have limited to 2 gigahertz. And you can see here that everything is good. So my device is certified. But on the same time, I have considered that all the signals on my USB are synchronized. There's no delay on time. And here my CPU is working 100% ideally. But what if I consider a worst case scenario where I even have here, you see, I have a small delay between, you see here in my USB, if I just go back a little bit to before, here, you see I have 2 traces. So I have 2 signals, each one going on each trace. So the thing is now, if I have considered, as I showed you here, that I have a small delay, because why we may have a delay? As I told you, it could be a default of the CPU, but also it could be a difference in length, because usually those length of the traces, they need to be exactly the same. If they are not the same, there will be a delay. It means that one information is being received faster. This is, if I want to ease it for you, it's like that. So even introducing this small delay, it will push your device to not be certified at all. So this is the reason why people, when they want to certify their product, they go like worst case scenario. Okay, so basically my device is not certified here. So I need to do something. So you may have seen that if you open up an electronic products nowadays, you may find that some, some traces, we have some, electric shielding, so some metallic shielding on them in order to imprison the field inside and not to be radiated. Okay. Good. Now I'm going to pass to the last part of this presentation. But before of that, as I told you, EMC, it's very wide, sorry. And, a type of EMC study is the lightning strike analysis, because aircrafts, they need to be certified to see if they can stand an a lightning strike, because lightning strike, they hit an aircraft at least once a year. So we have to make sure, because we have here like 200,000 amperes that are being injected inside our aircraft. So we need to be sure that all the electronics are immune. Again, for in electronic warfare, for example, this is an Apache aircraft, and we wanted to study the immunity of this aircraft versus an electromagnetic pulse bomb. And here it's a good real case example, because this client was Google, and they wanted to see if their data center is protected versus all type of electromagnetic activity, whether it's intended or not. For example, if you have a storm happening around the data center, a storm is an electromagnetic phenomenon. You see all the lightnings, etc. Those are some electromagnetic phenomenons, and they are very strong, and they could reach your data center. And this is why Google, they wanted to study, or they wanted to design a shielding around the building. And this is why you can see here some wire mesh inside the concrete. And finally, we have the electrostatic discharge as well. When you touch your finger, sometimes if it's humid enough or very dry, you may feel a spark in your hand. So if this spark reaches the electronic product, it can KO it. And this is why we need to study the immunity of our electronic products versus electrostatic discharge. And this is why you can find a lot of devices that are protected. You see, you have some circuit that actually mitigate the electrostatic discharge signal and protect your electron products. Okay, I'm gonna pass like quickly to this most exotic domain. And really here, I'm gonna stay on the surface, because I don't want to provoke a headache to any one of you today, but I will just fly over the application, because I'm pretty sure that you have a lot of application. You didn't even know that this is electromagnetics happening in there. So first of all, we have high energy sources, right? And the high energy sources, I'm gonna give you one example. It's your microwave oven that you have at home. What is the component that is behind generating this high energy? We call this the magnetron. And the magnetron, it's based on on particle simulation. So you see here the particles such as electrons, they are accelerated by an external magnetic field. And inside the magnetron that you have in your oven, it's magnets. We have magnets inside again. And those magnets, they accelerate the electrons that are inside the magnetron. And the fact that those electrons are super, super, super energetic, this is equivalent to a very high energy. And this is how the energy that you inject inside your microwave, it's very high. You know, sometimes it's 1 kilowatt, sometimes 2 kilowatts, etc. But again, those kind of devices, they could be used in electronic warfare. As an example, this is a Vercator. And the Vercator is actually an electromagnetic pulse bomb that could be placed on a missile, for example. You see, it's non-explosive weapons, but they are here only to knock out all electronic products. Okay? Now, we do have other applications. For example, we have the X-ray tubes. You know, the X-ray designers, we have a lot of our users that use our tool to design their X-ray imaging machine. How an X-ray might work, you see here we have a tungsten filament. And when you inject a high current here, you know, you are heating up this filament and you are releasing electrons. So you see here the electrons, they are released from the filament under the effect of the temperature. And those electrons, they are accelerated again by a field. And finally, those electrons, they hit a target that is probably also made of electrons, of tungsten, sorry. So the fact that they hit this target, they will reduce the energy. You know, some energy will be absorbed and it will be translated into a light or into a photon or into an X-ray. And this is why I create X-ray. Again, if we have a musician among us today, this is a valve or what we call a lamp. You see, for those who have used lamp amplifiers, the design of the lamp amplifier is based on particle dynamics. And this is why we are speaking here about high powers. And this is the reason why lamp amplifiers, they withstand much higher power than the solid state amplifier, you know, of transistors or whatever. And again, I spoke to you about the magnetron, and this is how it works. You see here the particles, they are accelerated in a rotating movement. And here we have a traveling wave tube, and it's basically an amplifier where the energy of the accelerated electron is transferred to the radio frequency signal. And this is how you create an amplifier. Again, I have here a very exotic application.
Oh, Hassan, it appears that we may have lost the audio on your side. Yeah, it looks like we have lost audio from Hassan's side. We will see if we can get that restored. Hi, Hassan. It looks like we lost you there for a moment.
Yes, guys, can you still hear me? I'm sorry, I think.
I can hear you now. Yep.
Okay, perfect. Let me share my screen again, okay?
Great, thanks. Sorry, everybody.
Yep. All right, can you see my screen again?
Yes.
Okay, perfect. So this is where you have lost me, right?
Yes, that's correct. Yep.
Okay, so I'm gonna repeat that, no problem. So here, guys, I was saying that we have a lot of devices that still use the CPD, the charged particle dynamics, such as X-ray tubes, valves that you can see in lamp amplifier. For example, for guitarists who use lamp amplifier, they can stand much, much more power than the solid states amplifier, you know, of transistor base. And this is the magnetron I talked to you about before that you can find in microwave oven. And here we have an amplifier that is used a lot in space applications, where the energy that of the electrons, because here we have electrons that they are accelerated by an external field, and the energy of those electrons are transferred to the radio frequency signal. You see, and this is how you create an amplifier for your signal. Now here, as I was saying, that this is a very exotic application because we are dealing with plasma. You know, particle dynamics could lead to the plasma study. What is the plasma? In a nutshell, a plasma, usually it's a gas. So for example, you have the hydrogen, argon, whatever. When you bombard this gas with high energetic electrons, you are actually extracting other electrons from the atoms of the gas. And when you extract an electron from an atom, you are literally leaving an ion, what we call an ion. So when your medium that is made of gas is fully ionized, you are literally creating a plasma. Now, here I'm presenting two applications for a plasma. The first one is the thruster of this CubeSat. So what is going on here? We are ionizing the gas that is inside the reactor, and I'm leaving ions. And the ions, as I told you, they are positively charged. So here at the back of the reactor or of the thruster, I have a negative DC bias voltage that will attract the ion. So you see here, I'm extracting the ions, and this is what we call the action. And as a reaction, you are creating the thrust for your CubeSat. And again, here, this is a plasma reactor that is used for semiconductor etching, for example, or even like a material deposition, because we can use the dry etching or what we call the DC sputtering, sorry. And if you have any question about that, do not hesitate to let me know. I will definitely help you. And again, as I told you, you see here, I have the fields. You know, this is the electromagnetic field that is created inside the cavities. And those cavities, the distance between the cavities, the sizes, the opening here, the irises between the cavities, all of those components, they are optimized in order to make the electron behavior that you can see here. You see the electrons in the beginning, they are accelerated. Look how they gain energy when they go through cavities. You see the energy is increasing in electron volts, yeah? They reach the end with a very high energy here. And those cavities, they need to be well optimized in order to avoid all kind of reflection here. You see, so these cavities, they still do need a little bit of optimization, let's say. So first application of this kind of accelerator is this. This is a medical machine that is used to treat cancer, because the idea is that instead of accelerating electrons in this accelerator here, we are accelerating ions. And those ions, we can orient them towards the cancerous tissue in the human body, and we can heal cancer with this. But other type of accelerators, as I told you, we call this the Hadron Collider, which is in Switzerland. And usually we use that for scientific experiments, which, for example, it's until like 3 or 4 years ago, they managed to break electron and to see what is the sub-electrons. And this is where they discover the bosons and the spins and all of that. So those guys, they are literally studying the origin of life, okay? And this is one example of the studies we can make. Now, my final example that I would like to show you about that is what we call the corona and the multipactor. So let's start with corona. If you are lucky enough to walk one day in a rainy, let's say, day outside, by night, of course, or even when it's humid, very much humid. What you can see here, guys, it's a line, it's a high voltage line. Okay, let me do this. Yep, it's a high voltage line. And when you have the good amount of pressure, you know, because here we are at atmospheric pressure, you see here on Earth, but sometimes you can be at other type of pressure. That's, you know, there's no limitation. So if you have the good pressure, if you have the good air temperature, and if you have the good, let's say, conductivity, you see, if it's humid, some electrons on those high voltage line are released. You know, they could definitely leave the solids here, you know. And as I told you before, when you hit the gas. For example, here on Earth, we have a gas which is basically made of azote, right? So this is the main component, but of course it has a little bit of oxygen, hydrogen, etc. So anyways, those electrons, when they hit the gas, they ionize it. And as I showed you before on this application of the reactor and the thruster, depending on the type of gas, there is some glow that you can see. You see here, it's like azure, it's blue, it's very light blue, and here it's purple. And what is happening here is actually that you are ionizing, you are locally ionizing. You see where the electrons are moving, you are ionizing the gas, which is the air here. And you can see this effect that we call corona discharge. And this is why we need to fight this corona discharge, because, you know, if you lose electrons, you are literally using the energy from your high voltage line and you are reducing the efficiency. And this actually could literally be simulated, as you can see here. Here, it's not a high voltage line. It's another type of structure. It's a filter. It's a cavity filter, which is filled with argon gas. And you see here, we have under the pressure, because of the pressure, you know, of the gas and the temperature that is inside, etc., you can literally simulate where you have this localized corona discharge. And this is pretty awesome, guys. Now, if you are in space, so you are here in vacuum, we have no gas. Corona couldn't happen, right? Because there's no gas to be ionized. But what happens here is another phenomenon. It's called multipaction. What is multipaction? Again, you are here in vacuum, and because again of the high power, when all the when everything is let's say is here, I would say this, you may release electrons again from the structure. You know, for example, from this wall here, I can release some electrons, and those electrons, they move freely in space, right? So first of all, I have no ionization. But those electrons that are here, they are super energetic. They can come here and they can hit other walls, other metallic walls of the structure. And this will help of releasing other electrons, you see? And then the electrons that I have released from this wall, they hit other walls and they release, etc. So if we have a high power enough, a power that is high enough, we can create here what we call an avalanche. Because when you have a lot of electron moving back and forth here, extracting a lot of electrons, you are creating literally a current, you know, because what is electron moving like this, you know, from top to bottom? It means that you have a current that is flowing from the bottom to the top. And if you have a current that's flowing like this, it means that you have a short circuit. And it means that you have an arc here inside your device. And it means your device is not even working anymore. So again, this is something that the users, they need to fight, because all the space component manufacturer, they need to run this study. Because guys, if your device is out of service in space, I'm not even gonna start by telling you what they need in terms of time and money and investments to, you know, to make it work. So this is why it's much, much better to predict what is the maximum power that could be used on the device before it could break down. Cool. And I think by this slide, I have covered everything I wanted to show you today. So as Roland said in the beginning, if you have any questions, please do not hesitate to get in touch with us. We will be glad to show you, because I'm really, what I showed you here is like probably 20 to 30% of what we can do with the tool. We can have a lot of other applications. So if you have some interest, please do not hesitate. And I think, Roland, I'm going to pass the mic to you.
Great, thank you. Well, thanks again, everybody, for coming to the webinar today. I hope that all of you got as much out of it as I did. Thank you, Hassan, for the amazing presentation. Really appreciate it. I certainly learned a lot. And yep, if anybody has any further questions, feel free to reach out to us. Again, you can reach me at Rollin, that's ROLLIN .Willis, WILLIS, at 3DS, the number 3, the letter D, the letter S.com. So Rollin.Willis at 3ds.com. Thanks again. Hope everybody has a great day. Appreciate your coming, and have a great one.
Thank you, guys. Talk to you soon.
Bye for now. Bye-bye.